Hello, this is Jack Jackson. In this playlist, we have been examining triangles and their properties. In particular, we've been focused a lot on this idea of what are enough conditions to guarantee that two triangles must be congruent. And the crux of the matter was looking at when you had three uh, parts that were corresponding and congruent. That led us to six different conditions: side, angle, side, angle, side, 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 angle, side, angle, and angle. And we looked at these in each of four geometries: Euclidean, hyperbolic, spherical, and taxicab geometry. So our first question is, what conditions are needed to guarantee that even a triangle exists of that type? And if you look in the side angle side condition, there are no restrictions whatsoever in any of the geometries. If you give me two side lengths and an angle measure, no matter which of these three geometries, I can make at least one triangle, at least one congruence class of triangles out of that, perhaps more, depending on the geometry. When you're looking at the angle side angle and the angle side condition, the Euclidean, hyperbolic, and taxicab geometries, well, let's start with Euclidean and taxicab. Euclidean and taxicab geometries, the sum of the three angles, the interior angles, must be exactly pi or 180 degrees. In hyperbolic, the sum of the three angle measures must be less than pi, less than 180 degrees. So if you start with two angles that are already add up to pi or more, and their measures add up to that, then no such triangle is possible. So we must have at least strictly less than pi for the sum of the two angles that you're given, angle measurements you're given. For spherical geometry, that restriction doesn't apply because the angles are already going to be bigger than pi for the sum, and they can be any proper measurement for the two angles, and you can still make a triangle. For the side condition, you must obey the triangle inequality. So for Euclidean, hyperbolic, and spherical geometry, the triangle inequality says the sum of the lengths of the two shortest sides must be strictly greater than the length of the hypotenuse, the length of the longer side. Or more generally, the sum of the lengths of any two sides must be greater than the length of the third side. Now in taxicab geometry, it's almost that, but here, the sum of the lengths of the two shortest sides must be not strictly greater than, but greater than or equal to the length of the hypotenuse. So just a slightly less restrictive version of the triangle inequality. Okay. If we have let's go to the angle situation. The sum of the three given angle measures, again, must be equal to pi for Euclidean and taxicab. It must be less than pi for hyperbolic and greater than pi for the spherical geometry. If you have that, then you will get at least one congruence class of triangles. In fact, yeah, you'll get at least one. Depends on the geometry if you'll get more than one or not. The side angle condition kind of depends on the length of the first side compared to the relative angle and side length of that adjacent side. So if the first given side must be long enough, specifically it must be greater than or equal to the given adjacent side length times the sine of the given angle measure. Okay, and I'm not going to give the exact conditions for the others, but you get a similar situation for hyperbolic, spherical, and taxicab. The first given side length must be long enough compared to these others. I'll just leave it at that and be vague about it. Okay, so what we're going to do is we're going over our conclusions of things that we've already found. We are assuming here that the given angle measurements are for proper angles, that they're all in the interval from 0 to pi radians or 0 and 100 degrees, not including 0 or pi. No straight angles are zero angles. We're also assuming that we've given proper measurements for the lengths of the sides. For Euclidean, hyperbolic, and taxicab geometries, that would be anything from 0 to infinity, any positive measurement, not including 0. And for spherical geometry, that must be something in the interval from 0 to pi for spherical geometry. These are not any kind of special conditions, so I'm not talking about those above. Notice that the SAS condition is the only one that it's always possible to construct at least one triangle, regardless of which geometry you're in, no matter what and regardless of which measurements you pick. Any measurements that we pick for AAS and ASA conditions always will result in at least one triangle in spherical geometry as well. Triangle quality is the same for all four geometries, almost. Let me see, almost the same. The sum of the measures interior angles must be less than or equal to pi equals 180 in Euclidean taxicab and hyperbolic geometries, so that puts a restriction on the AAS and ASA cases. Restrictions don't apply to spherical geometry where angle sum is somewhere in the interval from pi to 3 pi. Next, what are possible triangle measurement conditions? What are the possible number of congruence classes? So again, we're looking at these same 6 scenarios, SAS, ASA, SSS, AAS, AAA, and SSA. And we're looking at Euclidean, hyperbolic, spherical, and taxicab geometry. Of course, this table could be put together, arranged, rotated, or it could be put together in some different order of the columns or rows. So be sure, if you're learning this, say for my class, that you actually remember what goes where and not just where its physical location is in the table, because I could scramble it around a little bit on an exam. Given all triangles with the indicated set of some specific measurements, depending on the values of those measurements, how many congruence classes are possible? Well, notice the ones. The SAS is the only one with one that doesn't have a zero case there. The only other one that doesn't have a zero case is the taxicab. That's still SAS. And then spherical geometry doesn't have a zero case here or here. But the only ones that are just ones only is the SAS for Euclidean, hyperbolic, and spherical. Notice that every single case here for taxicab has an infinitely many case. So none of the criteria work there, and so forth. Another one, so remember sort of the ones that don't have zeros are these for SAS, and then the two angle ones for spherical, this one and this one. Okay. Now, so we went over all those details in the earlier videos. Again, notice that the SAS is the only one with a triangle always possible in exactly one equivalence class regardless of given measures in Euclidean, hyperbolic, and spherical. So now, what if we switch the question around slightly and say given two triangles, so the two triangles actually exist, and they're given the indicated corresponding parts are congruent, even though we may not know what the lengths are or the measurements are, do the two triangles have to be congruent? And again, we're going to go side, angle, side, angle, side, angle, side, 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 angle, angle, side, angle, 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 and side, side, angle for Euclidean, hyperbolic, geometry, spherical, and taxicab. And the first thing to notice here is that taxicab was no all the way across, and side, angle, side is no, is no all the way up and down. So really, there's only two other no's to keep track of if you've got that worked out. It was the angle, angle, side situation, and thinking spherical, our counterexample there is where we had a triangle going from the North Pole to 2 points on the equator. Those 2 points on the equator could move around and get different sized triangles there. Okay, and the Euclidean geometry, the angle, angle, angle was the other one, and we know that that gives us, with our infinitely many different similar triangles that are not necessarily congruent, but they'd have all of the same angles. Okay, and so really it's pretty simple to memorize this table if you could just remember a couple of basic facts. SSA, and by the way, it's the only one that spells a word. Read it backwards. That and that don't work. Taxicab is weird. It's the one that's strange compared to the others, that nothing works for that. So let's look at some similarities and differences among the different geometries here. Okay, notice that SAS ASA, SSS, and SSA conditions in Euclidean hyperbolic and spherical geometries behave the same. Okay? And all three of these geometries, SAS, ASA, and SSS, are enough to guarantee congruence of triangles. Also, in all three geometries, SSA is not enough to guarantee congruence. The SSA always includes the possibility of the ambiguous case, which we'll examine a little bit more below, but that's where you have two possible congruence classes. In both Euclidean and hyperbolic geometries, the AAS condition is enough to guarantee congruence. In spherical geometry, the AAS is not enough to guarantee congruence in triangles. In Euclidean geometry, the AAA condition is not sufficient to guarantee congruence in triangles, but the AAA is enough. Well, it produces similar but not necessarily congruent triangles in Euclidean geometry. We're going to come back to similarity a little bit down the road in a later playlist, a later chapter. However, in hyperbolic and spherical geometries, the AAA condition is enough to guarantee the congruence of triangles. There are no non-congruent similar triangles in hyperbolic and spherical geometries. Therefore, in hyperbolic geometry, the only one of the six possibilities which does not guarantee congruence of triangles is the one that spells a word backwards, SSA. Let's talk about some differences. In regard to triangle congruence, taxicab geometry is an entirely different beast altogether. None of the sets of three congruent pairs of corresponding parts is enough to guarantee that triangles are congruent. In fact, the examples that we've seen show that the only congruence criteria short of knowing all six parts are congruent that actually turns out to guarantee the triangles are congruent in taxicab geometry is the SASAS condition, where we conclude that the remaining pair of angles in fact are congruent. So basically you're saying all the corresponding parts are congruent except you're not sure about one angle. Well, you have the triangle angle sum theorem for taxicab. So if you get two angles congruent, you're going to get the third one as well. That's the only criteria short of just showing all six parts are congruent that will get you congruence in taxicab geometry. In fact, the main reason we study taxicab geometry is because of this difference in how it behaves in regard to triangle congruence criteria and what that has to say about the side angle side postulate, that it's independent of the others. Differences in spherical geometry. With the exception of the AAA condition, even though they look differently, triangles in Euclidean and hyperbolic geometries behave basically in the same way, at least as they relate to congruence properties and their consequences, such as all the theorems in this section, right? The only exception, with one exception, and that is the existence of the AAA congruence property in hyperbolic geometry, which does not exist in Euclidean geometry. In many respects, spherical geometry triangles behave similar to those in Euclidean hyperbolic geometry, especially if the sides are all shorter than pi over 2. In other words, the triangle fits into one octant of the spherical plane. Some serious differences occur when we make the triangles with side of length pi over 2 or longer, specifically the exterior angle inequality and the AAS congruence theorems fail. And even though the SAAS, I think I may have called it AASS earlier, but SAAS is another way to say it. SAAS, that's not the right. It's AA. It's ASSA. No. SAAS, I guess works, or AAS, SSAA. Let's call it that. It's the same thing. That condition fails to produce congruent triangles in spherical geometry if the sides are too long. Remember that we had a tri-right triangle counterexample. That one along with another one that was similar. All right, let's look at a few more things. In hyperbolic and Euclidean geometry, knowing 4 or more corresponding pairs of parts are congruent is enough to guarantee that the two triangles are congruent. And that's true since any combination of 4 or more corresponding congruent parts results in at least one of SSA, ASA, AAS or SAS being true. And if you're not sure about that, convince yourself this is true. In spherical geometry, knowing SAAS, or what did we decide we were going to call it? SSAA, is not enough to guarantee the two triangles are congruent, which we can see by the counterexamples that we listed earlier. Any other combination of 4 or more non-corresponding parts congruent is enough to guarantee the two triangles are congruent in spherical geometry. In spherical geometry, knowing any 5 corresponding parts are congruent is enough to determine the two triangles are congruent, since it forces one or more of SAS, SSA, ASA, or AAA to be satisfied. In taxicab geometry, nothing short of SASAS is enough to determine the two triangles are congruent. So what's the minimum number of corresponding congruent parts, regardless of the specific part, required to guarantee the congruence of triangles? And Euclidean geometry, once you get 4, you're definitely there. 3 may not be enough if they're not the right 3. Same for hyperbolic geometry. For spherical geometry, once you get to 5, that's definitely enough. Oftentimes you can get by with 3 or 4, but there is one case where 4 is not enough, so 5 would be it. In taxicab geometry, there is one specific situation where you know everything but one angle where 5 is enough, but in general you're going to need 6. What's the minimum number of corresponding parts if they're the right ones that are required to guarantee the congruence of triangles? Well, Euclidean geometry would be 3. If you have 1 or 2, no way you can guarantee the triangles are congruent. But if you have SAS, ASA, AAS, or SSS, that's going to be enough for Euclidean. You have exactly the same ones for hyperbolic geometry, SAS, ASA, AAS, and SSS, but you also have another one, AAA. Spherical geometry, you have the same ones as hyperbolic, but throw out the AAS. So it's 3 is enough if you have SAS, ASA, SSS, or AAA. And taxicab, the only one that you could possibly do with less than 6 is 5, but you specifically have to have SASAS. Finally, I've got a note about corresponding parts. I have another video. We'll look at this later in the similarity section. But the word corresponding is important. Okay? Notice that in Euclidean hyperbolic geometry, knowing any 2 corresponding pairs of angles and any one pair of corresponding sides are congruent is enough to guarantee that the triangles are congruent. Okay. However, even in Euclidean geometry, it is possible to have 2 triangles with 1 pair of congruent sides and 3 pair of congruent angles which are not congruent, if we do not insist that the parts are corresponding. There can even be 2 congruent triangles with measures of 5 parts that are congruent, but the triangles are not congruent. And here's a pair illustrated here. So notice in this example, angle C prime is congruent to angle C. This angle here is congruent to the one let's see. This is congruent to, I think, the one up here. This one is congruent to that one. So we get some congruent angles. And then the blue sides are congruent and the red sides are congruent, but then the green sides, the black and green sides here are not congruent. But they are not corresponding. Like if you make this C corresponding to here, right? And this angle A corresponding to the angle A up here, and the B to the B here, that will get all your angles corresponding and congruent. But then whenever you turn around and look at the sides, the side A here is corresponding to this side here, they're not congruent. This side here corresponds to this one here, they're not congruent, and this one here corresponds to this one, and it's not congruent. But we do still have 5 not corresponding, in some cases, congruent parts. So the word corresponding is important. All right. Um, all right. I think that's a good summary of what we've done so far in our investigations. So we have investigated triangle congruence. We have seen that we had to accept side angle side as a postulate, and we have proved the uh, angle side angle, angle side, exterior angle theorem, the isosceles triangle theorem, and the side 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 congruence theorems.